In the course of solving a energy balance problem, as we've seen so far, we oftentimes have to calculate the change in enthalpy or internal energy of a particular substance. And the most accurate and easiest way to do so is by consulting a table of thermodynamic data. An example that we've already seen in this class are the steam tables. In your textbook, they're table B5, B6, and B7. And that is because water is so common and so studied that we can devote that many pages in our textbook. 3 tables are devoted to just that one chemical at a range of pressures, temperatures, and state of matter. However, there are some other common chemicals that we might see. And for those, we can go to table B8 and B9. These are the next couple of tables in your appendix. And note the titles of the tables. It's called Specific Enthalpies of Selected Gases. Notice that they're the same exact gases in both tables. The only difference is that table B8 is for SI units. In other words, temperature is given in degrees C. And the energies are given in kilojoules per mole. In contrast, in table B9, this is for English units, where T is given in degrees F and H hat is in BTUs per pound mole. So depending on what units you're working with in your problem, that will inform whether or not you should use table B8 or B9. A couple of things to notice about this table. The first thing that jumps out at me is that water is on this table as well. And if you would like to compare table B8 to table B7, you can do so. The only thing you need to be aware of is that this water is for water vapor or gaseous form of water. And the other thing is that the reference state of the table is different. So the reference state of the table is labeled clearly at the top. 77 degrees Fahrenheit for table B9 and 25 degrees Celsius for B8. So if you would like to compare the results from table B8 or B9 to any of the steam tables, you have to be aware of the fact that they use a different reference temperature. So you must take that into account if you wanted to mix and match the results of these tables. I think it's probably safest to just use one table or the other. But that's not to say that if you use the steam table in one part of the problem, that you can't use table B8 to determine the enthalpy change of nitrogen, for example. So you can mix and match, and you can set a reference state for each species individually. So it is permissible to use the steam table and therefore set the reference state of water to be the reference of the steam table, and at the same time use table B8 to calculate the enthalpy change of nitrogen and thereby set the reference state of this table, 25C, as your reference state of nitrogen. Another thing to notice is that I have table entries for 0 degrees C and correspondingly 32 degrees Fahrenheit in table B9. The values here are negative, which, remember, it doesn't make sense. You cannot have negative energy. However, in order to quantify the energy at all, remember that it has to be relative to a reference state. So just as the title of the table suggests, this reference state is 25 degrees C, and here arbitrarily is where we set the values of the energy equal to 0 for all of the components. So therefore, it's improper to say that air, for example, at 0 degrees C, has an energy of minus 0.72 kilojoules per mole. You always have to remember that the enthalpy of air is negative 0.72 kilojoules per mole relative to air at 25 degrees C. So once again, it's always imperative that you keep in mind what your reference state is and recognize that the energy values or the enthalpy values that you see are never going to be taken on an absolute basis, but they're always relative to some reference state. The other thing to notice about these tables is that enthalpy is increasing as you increase in temperature, which makes sense. A compound will have more energy or enthalpy as the temperature increases. And the other thing to notice is that I don't have many data points here. So I have a gap of 100 degrees C for the most part, except for 25C. Therefore, if I want the enthalpy of a gas at 325 C, for example, that would mean that I would have to use a linear interpolation once again. It's improper to just take the average or to take the data point of the data point that's closest. So for example, if I wanted air at 320 degrees C, it's improper to just round 320 to 300 and call it 8.17. You would not want to do that. You want to use the interpolation formulas once again. Other than that, there's not really much to table B8 and B9. I think the hardest part about table B8 and B9 is remembering that they exist. And for that, I would just suggest that anytime you have a common gas, so notice that these are all common gases. So we've got oxygen and nitrogen, which are the two main components that make up air. And you should notice that the enthalpies of air are always in between that of oxygen and nitrogen. So for example, 14.37 is between 15.03 and 14.24. It always tends to shade onto the side of nitrogen because air is primarily nitrogen. We also have hydrogen gas, carbon monoxide, carbon dioxide, and water vapor. So these might all seem familiar from your combustion reactions. And anytime you have a combustion reaction stat gas that needs to be cooled or something, your mind should immediately be thinking of table B8 and B9. So my best advice is just try not to forget that these tables exist, because in many cases, figuring out the changes in enthalpy or internal energy, once again, will be much more accurate and easier if you use these tables as opposed to the methods that we'll talk about in the coming couple of videos.